All right, we're back. We're on page 123 in math analysis. We're talking about vectors, adding, subtracting, scalar multiplying, magnitudes, just like everything, basically. And then we were talking about lines and how we could work with lines. Lines contain an infinite number of points, and since they contain an infinite number of points, we can make an infinite number of vectors. But then we thought it through, and we thought every time we make a vector using 2 points on any particular line, it's definitely just going to be parallel to any other vector that we make, which means they're going to be scalar multiples of each other. That has to happen, right? Because the line contains all these points that are in a line, right? And the line is dictated by its slope, really. And we saw a little connection between the vector and the slope. And now what we're going to try to do is write the vector equation of a line. So we want the vector equation of a line that's going to go through the points -2, 5, and 4, 3. So we're going to do this by example. But the idea is very general. So it doesn't matter what the points are, the process will be the same. So what I'm gonna do is I added a page here so that I could just kind of draw without worrying about, running over other stuff. So let's see, this is my line, right? And this has the point -2, 5. And then it has the point, what was the other point? 3 something? 4, 3. Okay, so this will be the point 4, 3. All right, so what we are claiming is that if I take any point on this line, so if I take this point, for example, and I'm just going to say this is the point x, y. If I make 2 vectors right now, so the first vector that I'm going to make, I think kind of clearly should be this vector from here to here, right? I'm going to make that vector. And I'm going to call that, I don't know, I'm going to call that v, I guess. So v. Now v is going to be the vector 4 minus -2 is 6, and then 3 minus 5 is -2. So I can use any scalar multiple of that, though. I could use 3, -1, which is actually what I prefer to use, because if there's a common factor, I like to get rid of it, because it just scales your vector down. All your calculations are a little easier. But whatever, I'll leave it the way it is now. So this is v, and if I make another vector, so the other vector that I make is going to be a little weird. I'm going to make the vector, what color should you be? I'm going to make the vector, I guess I'm going to make this one. You know what I'm going to do? I'm going to pick up this point and move it so that it's a little clearer. Oh no, why are you moving the whole thing? Hold on, hold your horses. Let's move this there, and then I really need to copy. There we go. But where am I going with that? Okay. I'm setting this up it shouldn't really matter where I put it, but I think that it's easier to follow if I put it where it is now. I'm gonna make this vector from here to here. And that, okay, so now that vector, I'm just going to say it's a generic vector. So xy is any point that's on the line. This vector will have x's and y's in it, right? It's going to be x minus 4 and y minus 3. So the terminal point is xy, the initial point is 4, 3. I could have used the other point. I could have used -2, 5, and then it would have been x plus 2 comma y minus 5. It doesn't make a difference. Think of how point slope form works. It doesn't make a difference what point you use as long as it's a point on the line. Same thing here. It doesn't really matter what point on the line you use. You need your generic point, right? So we have a generic point, xy, and then you have your specific point of 4, 3. But we could have used this specific point, -2, 5. It wouldn't have made a difference. What we're claiming is that these 2 vectors, since they're both from the line, they must be scalar multiples. So these 2 vectors are scalar multiples, which means that x minus 4, uh-oh, where are you going here? What is happening? All right, I got it, don't worry. Okay, so this is an idea. Should have been a different color, but x minus 4, y minus 3 should be a scalar multiple. So a scalar multiple, we'll use k for our scalar, or t. Let's use t. T times 6, -2. This is by definition of parallel line of parallel vectors. So this is all from definition of parallel vectors. So I'm gonna go back to the notes and like fill this in. But this right here, this is, oh my God, that is gross. Let's undo that. What can I do? I don't even know. There's like no color that is, well, maybe this. It's not terrible. This is the vector equation of the line. What? L-I-N-E. That's the vector equation of the line. What? Right? So it's a little weird. It's an equation that has two vectors in it. If I give you a t value, so I give you t. T can be any real number. So t is an element of the reals. I don't usually write that, but I probably should. So let me move this over and say comma, t is an element of the reals. So I tell you what t is, and then you can use this equation to find x and y, and that'll be a point on the line. It's a very weird kind of like definition, but it works. So let's go back and fill this in. So use the given points to make a vector. So we made our direction vector. So it's called a direction vector because it's the vector parallel. So we did 6, -2. So I usually will scale this down and just say this is going to be 3, -1. But it doesn't really matter. But I usually do that. So then we have x, y, and we used 4, 3. And we, 4, 3. And we created another vector. And that vector I think of as the generic vector. So we make a generic vector. And so the whole idea is that the vectors are parallel because they come from the same line. Any vector that I make using 2 points on this line, definitely going to be parallel to any other vector that I make using 2 points on this line. So I used the point xy, which is on the line, the point 4, 3, which is on the line, and the point whatever, -2, 5, which is on the line. So all of those are on the line. The two vectors I made must be parallel. By definition, parallel vectors are scalar multiples. So x - 4, y - 3. And we're using t. The reason you use t actually is for time. Like usually there's a time component involved here. We don't have that yet, but usually it's there. So I'm going to use 6, -2. So if I use 3, -1, every calculation that I have to do is like just easier by like a factor of 2. It doesn't really matter, but it's something to think about. Any parallel vector. So I could also use, I don't know, 18, -6. I could use -3, +1, right? Just multiply by -1/2, I guess. We can just scale it. So now t is called a parameter. So a parameter is not super important for us just yet. A parameter is a variable that connects other variables, right? So the truly independent variable up here is t. If I tell you what t is, you can figure out what x and y are. If I tell you what x is, like you can figure out what t is, and then when you figure out what t is, it'll tell you what y is. But if I just tell you t, it determines x and y. It is the parameter. It's like the independent variable. X and y are more dependent. So if we take this and we break it up using, so think about like your matrices, right? This is essentially x - 4, y - 3 equals 6t -2t, right? Well, that gives us two equations. It gives us x - 4 is 6t, and it gives us y - 3 is -2t. So what I can do is I can say x - 4 equals 6t, which means that t is x - 4 over 6. So that's one version of t, which I guess here. Also, I know that y - 3 equals -2t, which means t equals y - 3 over -2. That's another version of t. And then since they are both equal to t, they're equal to each other. So therefore, y minus 3 over negative 2 equals x minus 4 over 6. That's called the symmetric equation of a line. I hate the symmetric equation, but that's called the symmetric equation. And then another thing that we can do, so we have eliminated the parameter. That's what we just did here. So getting rid of t is eliminating, that might be spelled wrong, parameter. Sometimes I get lost in the middle of a word and there's like no yet now. Eliminating the parameter. All right, and then one last thing that I want to do here. So I want to take my y minus 3 over negative 2 equals x minus 4 over 6. I'm going to multiply by negative 2, get y minus 3 equals, so negative 2 over 6 is negative 1/3 x minus 4. Check that out. That, hopefully, you recognize. This is point slope form. So all of these forms are related. The vector equation is really useful. It's really fast to come up with, right? So we just kind of to summarize, we found one specific vector using 2 known points. Then we use a generic point and a known point to make a generic vector. And then those vectors must be parallel, which means that it must be the case that our generic vector is just t times our specific vector. And we got it. Like, that's the whole thing. One of the really nice things about vectors is that, like, everything is kind of built on definitions. So you can, once you know the definitions, you can kind of like work things out from there, which I really love. And then here's a little summary of that. But anyway, I'm going to stop this here. I will come back in the next one. And then, I don't know, keep going. So I'll see you there.